Let's now take a look at an example. So if we have some potential V equals x minus y plus xy plus 2z volts in some region, we want to find the electric field and the energy stored in a cube with sides of 2 meters centered on the origin. So of course, this problem is sort of guiding us in the right direction by having us find the electric field first, because our equation for energy depends on the magnitude of that electric field. So let's start by finding that electric field. So of course, we're going to use our expression that the electric field is the negative gradient of our voltage. And so because we have a Cartesian expression for our voltage, that's just going to be negative partial of V with respect to x in our x direction minus the partial of V with respect to y in our y direction minus the partial of V with respect to z in our z direction. So if we evaluate that, what we get is our E is equal to negative 1 plus y, and so again that's just the derivative of v with respect to x. So for instance, we have our 1 coming from here and our y coming from here. Nothing else has an x, so it all goes away. It's treated like a constant. That's in our x direction. We then have minus the partial of v with respect to y, so just scrolling up so you can see that. That's going to be negative 1 plus x, and then that's in our y direction. And finally, we have our partial of v with respect to z, which is just going to be a 2, and that's in our z direction. All right, so we can write that as E, and so let me just use my angle brackets to make this a little simpler. So here we have a negative y minus 1 in our x direction. We have 1 minus x in our y direction and a negative 2 in our z direction, and the units of that are going to be volts per meter. All right, so there is our electric field expression. So now what we want to do is we want to find the energy in that cube with sides of 2 meters centered on the origin. So we go back to our equation from the previous video. We say that the energy in the system is equal to 1/2, and I'm going to go ahead and pull out that epsilon naught because that's just a constant, times the integral over the volume of the magnitude of our electric field squared times our differential volume. All right, so we have our epsilon naught over 2, which is just going to be hanging out there for a while. And then we have our integral from z equals, negative 1 to 1. So each of our variables is going to be varying from negative 1 to 1 because that gives us our side length of 2 while centering it on the origin. So from 1, there we go. And so we have the magnitude of this negative y minus 1, our 1 minus x, and our negative 2. So the magnitude of that is going to be squared, and our differential volume is dx, dy, dz. So relatively simple in Cartesian coordinates. So let me just go ahead and copy this to not have to write that again. So we still have that epsilon naught over 2, the integrals from the three variables where we're varying, and let's go ahead and take that magnitude and square it. So of course, magnitude would be the square root of each component squared, but because we are squaring that, we get rid of the square root. So we're going to have a negative y minus 1 squared plus 1 minus x squared plus negative 2 squared. And then we still have our dv, which is dx, dy, and dz. And so at this point, what we can do is we can sort of break up this integral. So we can sort of factor this out. We'll be left with some constant terms. And so what that ends up looking like is we have our epsilon naught over 2, and then I'm going to multiply that by sort of all of these things I'm going to break apart. So we're going to end up with 4 times the integral from y equals negative 1 to 1 of y squared plus 2y dy. And so again, because there's no x dependence in that area, I don't have to keep that with my x and z integrals. I also get a 4 times the integral from x equals negative 1 to 1 of x squared minus 2x dx plus 6 times 8. All right, So the z integral we could go ahead and evaluate because we didn't have any z variable. So that's why we just have a constant there for that last part. All right, so then evaluating this, what we're going to get is we have epsilon naught over 2 times 4, and then we have y cubed over 3 plus y squared. And we evaluate that between -1 and 1, plus 4 times x cubed over 3 minus x squared, evaluated between -1 and 1, plus our 6 times 8. And so what we get then is if we plug in our value for epsilon naught and we evaluate all of those two items there, we end up with an energy in that cube, which is approximately equal to 0.236 nanojoules. So 10 to the minus 9th joules.